Hello, cosmic explorers. Welcome back to Cosmos K. Today, we're diving into the enigmatic world of black holes and uncovering some of their most shocking secrets. Join me as we journey to the very edge of space and time, where gravity reigns supreme and the laws of physics are pushed to their limits. Imagine a place where time itself slows to a crawl, where minutes stretch into millennia and the very fabric of reality distorts. That's what happens near a black hole, a region in space-time where gravity is so strong that nothing, not even light, can escape its grasp. This mind-bending phenomenon, known as time dilation, arises from Einstein's theory of general relativity. Picture space-time as a flexible sheet, and massive objects like stars and black holes as weights placed upon it. The heavier the object, the more it warps the sheet, creating a gravitational well that pulls everything towards it. Now, imagine two clocks, one placed far away from a black hole and another placed near its event horizon, the point of no return. As time passes, the clock closer to the black hole will tick slower than the clock farther away. This isn't due to any mechanical malfunction, but rather a fundamental consequence of the curvature of space-time caused by the black hole's immense gravity. Think of it like this. Imagine two hikers setting off on different paths up a mountain. One hiker takes a steep, winding route while the other takes a more gradual path. Even though they both cover the same horizontal distance, the hiker on the steeper path will experience a greater change in altitude. Similarly, time flows differently depending on the strength of the gravitational field. Near a black hole, where gravity is incredibly strong, time slows down relative to an observer in weaker gravity. This means that if you were to observe a spacecraft falling into a black hole, you would see it gradually slow down as it approached the event horizon, its image redshifting until it eventually faded from view. But from the perspective of the spacecraft itself, time would flow normally. At the heart of every black hole lies a boundary of unimaginable density and gravitational pull, the event horizon. This is the point of no return, a cosmic threshold beyond which nothing, not even light, can escape the clutches of the black hole's gravity. Imagine a waterfall, where water cascades over a precipice. As you approach the edge, the current grows stronger, making it increasingly difficult to swim against the flow. Eventually, you reach a point where the water's velocity exceeds your ability to escape, and you're pulled over the edge. The event horizon of a black hole is analogous to this point of no return. As light and matter approach the event horizon, they're inexorably drawn inward by the black hole's immense gravity. Once they cross this boundary, there's no turning back. Imagine approaching a black hole feet first. As you get closer, the gravitational pull on your feet becomes significantly stronger than the pull on your head, stretching your body like a strand of spaghetti. This bizarre and somewhat gruesome phenomenon, known as spaghettification, is a consequence of the extreme tidal forces at play near a black hole. Tidal forces arise due to the difference in gravitational pull across an object's length. Even here on Earth, we experience tidal forces from the moon's gravity, which is why we have tides. However, these forces are relatively weak compared to the immense tidal forces near a black hole. As you fall towards a black hole, the difference in gravitational pull between your head and your feet becomes increasingly extreme. Your body is stretched vertically, becoming elongated and thin like a noodle. For decades, black holes were thought to be inescapable cosmic vacuum cleaners, devouring everything in their path and allowing nothing to escape, not even light. However, in 1974, physicist Stephen Hawking proposed a revolutionary idea that shook the foundations of black hole physics. Black holes aren't entirely black after all. Hawking theorized that black holes emit a faint thermal radiation, now known as Hawking radiation, due to quantum mechanical effects near the event horizon. This radiation, he argued, carries away energy from the black hole, causing it to slowly evaporate over time. To understand Hawking radiation, we need to delve into the strange world of quantum mechanics, which governs the behavior of particles at the subatomic level. According to quantum theory, empty space isn't truly empty but teeming with virtual particle-antiparticle pairs that constantly pop in and out of existence. These virtual particles, which borrow energy from the vacuum of space, typically annihilate each other almost instantly, returning the borrowed energy. However, near the event horizon of a black hole, The intense gravitational field can separate these particle pairs before they can annihilate. One particle falls into the black hole, while the other escapes into space. The escaping particle carries away some of the black hole's energy, effectively reducing its mass over time. At the heart of most galaxies, including our own Milky Way, lie cosmic monsters of unimaginable scale and power, supermassive black holes. These behemoths, millions to billions of times more massive than our Sun, exert a gravitational pull that governs the motions of stars and gas within their galactic neighborhoods. Supermassive black holes are thought to form through the gradual accumulation of matter over billions of years, swallowing up stars, gas, and even other black holes that venture too close. As they grow, their gravitational influence extends outwards, shaping the structure and evolution of their host galaxies. These galactic giants play a crucial role in the evolution of galaxies. Their gravitational pull can trigger star formation by compressing surrounding gas and dust, while their powerful jets of radiation can regulate star formation by heating up and dispersing nearby gas clouds. One of the most compelling pieces of evidence for the existence of supermassive black holes comes from observations of stars orbiting the center of our Milky Way. Black holes present a fundamental challenge to our understanding of physics with a perplexing conundrum known as the information paradox. This paradox arises from the conflict between quantum mechanics, which dictates that information cannot be destroyed, and general relativity, which suggests that information that falls into a black hole is lost forever. According to quantum mechanics, information about a particle's state, such as its spin, momentum, and energy, is encoded in its wave function. This wave function evolves over time, but the information it contains is always conserved, even if the particle undergoes transformations or interacts with other particles. However, classical black hole physics suggests that once an object crosses the event horizon, it's lost forever, along with any information it carries. The black hole's properties, such as its mass, charge, and angular momentum, are all that remain, regardless of what fell in. This apparent loss of information creates a conflict with quantum mechanics, as it implies that the black hole's final state could be identical, regardless of what fell into it, violating the principle of quantum information conservation. The information paradox has puzzled physicists for decades, leading to various proposed solutions and interpretations. While black holes are known for their insatiable appetites, devouring everything that crosses their event horizons, their theoretical counterparts, white holes, are thought to be cosmic fountains, spewing out matter and energy into the universe. White holes, hypothetical objects predicted by Einstein's theory of general relativity, are essentially the reverse of black holes. While nothing can escape from a black hole once it crosses the event horizon, nothing can enter a white hole. Imagine a black hole as a cosmic sink where everything flows inwards. A white hole, on the other hand, would be like a cosmic source where everything flows outwards. While black holes are formed from the collapse of massive stars, the formation mechanism for white holes remains a mystery. Some theories suggest that they could be the other end of black holes connected by hypothetical tunnels in space-time known as wormholes. Others propose that they could be remnants of the Big Bang, spewing out matter and energy from the early universe. The immense gravitational pull of black holes, while daunting and destructive, has also sparked speculation about their potential as cosmic shortcuts for interstellar travel. Could these gravitational behemoths, warping the fabric of space-time, hold the key to unlocking faster-than-light travel and unlocking the secrets of the universe? One intriguing possibility involves wormholes, hypothetical tunnels in space-time connecting distant points in the universe. Some physicists believe that black holes, with their extreme space-time curvature, could act as gateways to these wormholes, potentially allowing us to traverse vast cosmic distances in an instant. Imagine a sheet of paper folded in half, with 2 points marked on opposite ends. A wormhole would be like a hole punched through the paper, connecting the 2 points and creating a shortcut through space-time. However, the use of black holes for interstellar travel is fraught with challenges. The extreme gravitational forces near a black hole would likely rip apart any spacecraft attempting to approach it, let alone traverse a wormhole. Moreover, the stability of wormholes is a major concern. From time dilation to spaghettification, black holes continue to challenge our understanding of the universe and inspire us to explore the unknown.